3 of x plus the log base 3 of 2x minus 1 in parentheses equals 1. Now, what does this mean? Well, it means that we have two numbers, both are log 3, base 3, log base 3 of x and the log base 3 of 2x minus 1. We add them up, we get 1. How do we solve this? Well, the way we said we solved a logarithmic equation is to make it into an exponential. But I can't make this into an exponential equation because there are two log terms. I need to be able to combine them. Well, how do I do that? Well, notice this is the log base 3 of something plus the log base 3 of something else. Remember that first rule was that the log of the product is the sum of the logs. Here is the sum of two logs, which means this represents the log of a product. This is the log base 3 of the product of x and 2x minus 1. So let's multiply that. X times 2x is 2x squared, and x times negative 1 is negative x. And that is still equal to 1. That is still equal to 1. Okay? What do we know? We now have a single logarithmic term, which we can take this logarithmic equation and change it into an exponential equation. That is the base to the power equals the number. In this case, the number is our x term, which is 2x squared minus x. So the base to the power equals the number. And guess what? We've lost our logarithms. We're not worried about x's in the exponent. We now have a quadratic equation which we know how to solve. We could solve it using the quadratic formula, but it turns out in most of these problems the answers will be rational, so we should be able to factor. Of course, the first thing we need to do is get everything on one side, ax squared plus bx plus c equals 0, factor and solve, and that's precisely what we do in the next visual. We see that we factored the 2x squared minus x minus 3 into 2x minus 3 times x plus 1 set equal to 0. As we've done before, we have two factors equal to 0. We set each factor equal to 0, and x equals 3 halves, or x equals negative 1. Notice the statement on the third line, which is highlighted. You cannot find the log base 3 of negative 1. In fact, you cannot find the log base anything of negative 1 because we said earlier we can never take the log of a negative number. And therefore, negative 1 cannot be a solution. And the reason is because the original equation has the log base 3 of x. We can't talk about the log base 3 of negative 1. So we disregard that solution, and it appears that the only possible solution is 3 halves. Does that mean it's right? Well, it could. We don't know until we've checked. And the next visual allows us to do that checking. Let's see, the log base 3 of x, which is 3 halves, plus the log base 3 of 2 equals 1. We replaced the x with 3 halves, and of course, to solve this, we go ahead and say, well, the log base 3 of 3 halves plus the log base 3 of 2 is the log base 3 of 3 halves times 2, which is the log base 3 of 3, which is 1. Why is it 1? Because 3 to the 1 equals 3. We can take our logarithmic expression, our logarithmic equation, and make it into an exponential, and that does check. Now let me get back to something I promised you would do, showing how to use your calculator to, as long as it has a log button, to find the log base b of anything. What we're going to do is use the LOG button on your calculator. And basically, let me go ahead over here to the easel and write down what the sort of formula is to do this. Let's say we want to find the log base b of a. Okay? We wanted to find the log base b of a. And this b was some number other than 10. And the log button on your calculator, LOG, is log base 10. What you would do is you would take the log of a, that is the log base 10 of a, on your calculator, and divide it by the log base 10 of the base b. Simple enough, it seems. And this is exactly what you do to get the log with any base using your calculator, provided, of course, your calculator has a log button. So let's take a look at the next visual, which starts off by saying we want to find the log base 3 of 3/2. We want to find the log base 3. For example, if we wanted to go ahead back and check that last problem, we needed to be able to find the log base 3 of 3/2. That's one of the parts of the checking equation. Well, according to what we had on the easel, we would take the log, log, which is log base 10 on your calculator, of 3/2, which turns out to be 0.17609, etc., and divide that by the log, log, of 3, which is 0.47712, etc. When we divide that, we get 0.36907, and that is a good approximation, at least rounded off to 5 places, of the log base 3 of 3/2. In other words, using your calculator and your log button, you can find the log of any positive number for any positive base. Rather simple to do. At this point in time, let's use the remaining time to talk about the graphs of a logarithmic function. Now, let's take a very simplistic logarithmic function. The y equals the log base 2 of x. And in fact, let's go ahead and look at the next visual, which shows us that function at the top and also reminds us that we can rewrite y equals the log base 2 of x as 2 to the y, the base to the power, equals x. And notice what I've done here in order to find points to plot, to graph this equation. I have filled in the y. You say, you can't do that. Yes, I can, because I just did. I filled in the y because I know that 2 to the y is x. And now I can simply replace the blank places for x by taking 2 and raising it to each of those y's. So, for example, when y is -2, 2 to the -2 equals 1/4. And in the next visual, we see we've done that. We've taken 2 and raised it to the y power and gotten the values of x. Again, remember the logarithm itself is the inverse operation of raising to a power. And therefore, we have put the y in to get the x. And now when you look at this visual and it says y equals log base 2 of x, if no one knew what you had done, it looked like you put the x's in and got the y's. Eventually, if you get really good at working with logarithms, you can do that. But there's no reason at this point in time to do that. If you have to graph a logarithmic function, write that function as an exponential function. And of course, you'll have x in terms of y, plug in some y values, and solve for x, and write the ordered pair x, y. Notice the x still is the first number, because when we graph these points, we're going to graph x and y. So in fact, let's take a look at the graph, which is on the next visual, the graph of y equals log base 2 of x. We've plotted the points, and you'll notice the graph looks somewhat like the square root graph. It rises fairly rapidly in the beginning and kind of levels off. And you'll notice we do have negative values of y, because when x is very small, like 1/5 or 1/10 or 1/100th, the log base 2 of a very small fraction is a negative number, since 2 to that negative number gives us a very small fraction. And you'll notice also that the curve is getting closer and closer to that y-axis, but it will never touch. Why will it not touch? Because we can never take the log of 0. We said that earlier, and therefore the curve y equals the log base 2 of x is asymptotic to the y-axis. Let's take a very quick look at something that's quite interesting over here at the easel. And if you can recall what the graph of y equals 2 to the x looked like. y equals 2 to the x started out over here and went through and came up like that, right? And the graph of y equals the log base 2 of x started down here, went through here, and went out like that. If we then dash in the graph of y equals x, which is a line like that, and again, I've just done it fairly quickly, you can see that if we take y equals log base 2 of x and reflect it or fold it over on this dashed line, y equals x, it folds right onto y equals 2 to the x. And that is because one of the characteristics of a inverse function is that it will be the symmetric reflection of its original function. So since log base 2 of x is the inverse of 2 to the x, it is the reflection. It is symmetric about y equals x. A very interesting thing, a good way to check that you found the correct graph for your inverse function. So in this a half hour, we have seen what a logarithm is. We've related logarithmic equations and functions to exponential equations and functions. We've seen how to solve logarithmic equations. We've looked at 3 very important rules in dealing with logarithms, and we've begun to look at how we graph logarithmic equations. Graphing of logarithmic equations will be looked at a later course, not any longer in this course, Algebra 2. The next lesson, Lesson 26, also introduces something you may not have seen before. It's matrices and determinants. That's not matrices and box springs. What are matrices and determinants? We'll see in Lesson 26.